A charge moving in a magnetic field experiences a magnetic force. A current-carrying wire consists of many individual moving charges, so a conducting wire that carries current must also experience a force when placed in a magnetic field. So assuming the charges are moving perpendicular to the magnetic field as they are shown here, the magnetic force on the charges is given by QVB. Now I'm going to take a given time t and say that the charges, so a current carrying wire is full of moving charges. I'm going to say these charges travel the length of this wire, L, in a time t. So the velocity I'm going to write for each charge has a velocity of L over t times b. Now in this expression here, this value Q over T is charge over time, which is electric current. And then the result of this, which is ILB, is commonly written as Bill, or B, electric field magnitude times I current times L, length of the segment of wire. Now this is assuming that the wire is flowing perfectly perpendicular to the magnetic field, which is often the case. If it's not, if the wire is flowing at an angle to the magnetic field, then in this case, there's an angle theta between them, and the formula becomes Bill sine theta. But most of the time, it's just Bill. So the magnitude of the force is given by Bill, BIL, and the direction can be found using the right-hand rule for the force on a moving charge. Conventional current is always going to deal with the direction of positive charges, so only the right hand is used here, where the thumb will point in the direction of the charge velocity, which is the current in this case. The fingers are the direction of the field, and then the force is directed out of the palm. Not only do conducting wires placed in a field experience magnetic force, but they also create magnetic fields themselves. Now, the magnetic field produced by one wire will not have a force on itself, but two conducting wires will exert forces on each other due to their magnetic fields. Here I have two wires flowing in the same direction. So wire 1 in blue, if I use the right-hand rule, my fingers will curl into the page below it. So wire 1's field is into the page in the region where wire 2 is. So if I use the right-hand rule for force on a moving charge, wire 2 has current to the right, so I'll point my thumb to the right and my fingers into the page with the field, and my palm points up. So the force on wire 2 due to wire 1 is upwards. Likewise, wire 1 will experience a magnetic force due to the field created by wire 2. By the right-hand rule for a field produced by a current, if I point my thumb in the direction of wire 2's current, my fingers curl out of the page above wire 2. So wire 1 is in a field that's out of the page due to the second wire. If I use the right-hand rule, fingers out of the page, thumb to the right, my palm points down. So wire 1 experiences a downward force due to wire 2. Whenever two wires have current flowing in the same direction, the two wires will have attractive forces towards each other. So conducting wires that have current flowing in the same direction will attract each other, or another way of putting it, if they flow together, they go together. For the magnitude of that force, I'll consider the force on wire 2 due to wire 1. So at wire 2, there's some field, B1, and that field B1 is equal to mu sub 0, I1, that's the current in wire 1, over 2 pi r, where r is the distance between the wires. So that's the field experienced by wire 2. And then the force on wire 2 would be the field that it's in, which is the field B1, times the current in wire 2 times the length. And putting that all together, that force is equal to mu sub 0 I1 times I2 times the length of the wires over 2 pi r. And because of Newton's third law, both wires will attract each other with the same force magnitude, but in opposite directions. Now the wires have current flowing in opposite directions, so I'll use the right-hand rule again for wire 1. Thumb to the right, fingers curl into the page where wire 2 is. Now I use the right-hand rule for force on a moving charge for wire 2. My fingers into the page, my thumb to the left, and my palm is facing down. So wire 2 has a downward force on it from wire 1's magnetic field. For wire 1, the force it experiences is due to wire 2's field. That field is into the page by the right-hand rule. And then since wire 1 has a field into the page exerted on it, if I use the right-hand rule for wire 1, thumb to the right and fingers into the page, my palm will be pointing up, so the force on wire 1 is up. And whenever two wires flow in opposite directions, they'll have forces opposing each other. So when conducting wires carry current in opposite directions, the two wires will have magnetic forces that repel each other. And just like when the wires are attracted, they'll have the same magnitude of that force, mu sub 0, product of the current, length over 2 pi r. And again, by Newton's third law, they're the same magnitude of force, but acting in opposite directions. Last, I put an example question here asking for the net force per unit length, or force per meter, on one of 3 wires. So I'm trying to find the force per unit length on wire A due to 2 other wires that carry current. So wires B and C will both create a magnetic field that act on wire A. So I'm going to find the net field first due to both wires B and C at A's location, and then use magnetic force equals Bill. So first I'll find the direction of the 2 fields. For wire B, the current is down, so I'll point the thumb on my right hand down. And when I do that, my fingers curl into the page. For wire C, now I point my thumb up. When I do that, my fingers curl out of the page to the left of wire C. Since they point in opposite directions, I'll find the difference of the 2 fields. And I get that the net field is mu sub 0 I over 3 pi r, and it's into the page, since wire B has a bigger field at the location of wire A. Now I want to find the direction of the force on wire A. So again, I take my right hand, point my fingers into the page, because the net field is into the page, and my thumb down. When I do that, my palm points to the left, so I know the net field is to the left, and the magnitude is equal to Bill, where I take the net field for the field acting on A. The current is I. Now the question asks for the net force per meter, so I don't have a defined length, so I'm just solving for force per unit length. And that's going to look like this, mu sub 0 I squared over 3 pi r.